Since this is a calculus class, we should definitely be talking about derivatives. So let's talk about the derivative of the inverse. We have a theorem that will give us a formula for the derivative of the inverse of a function f at a point A. Of course, we need our function to be a one-to-one function. So that's one of the requirements here. If f is a one-to-one function, and it is differentiable, that just means that it has a derivative. So if f is a one-to-one and differentiable function with an inverse, f inverse, such that f prime of f inverse of A is not equal to 0, then the inverse function is differentiable. At the point A, and we have a formula. So the derivative of f inverse, which we'll be known as f inverse prime, evaluated at A, this is just going to be equal to 1 over, you're going to take the derivative, and then you're going to find f inverse of A. So this is a formula that will allow us to calculate the derivative at a point. So the amazing thing about this equation is that, we don't have to find the inverse to actually find the inverse function. To get the derivative at a point. All we need to know is we need to know a couple things. We need to know, where did the point A come from? That's what the f inverse of A is. And we also need to be able to calculate the derivative of the original function f. What we do not need to calculate is f inverse itself. One thing I want to point out is we can see why we have this requirement that f prime of f inverse of A must not be equal to 0. The reason why we have this requirement is we don't want to have a 0 in the denominator of our derivative. Let's take a look at an example. Looks like I've forgotten to number this example, but I guess we'll get over it. So when we look at this example, the first thing we're going to notice is that f is one-to-one, and this is just it's a cubic function, y equal to x cubed function shifted down 1. So we know that shifting it down 1 is not going to affect whether it is one-to-one because it will still pass the horizontal line test. Okay. The second thing that we need to do is we really need to figure out what, we need to find what the inverse of 3 is going to be. So how do I do that? Well, what I'm going to do is I'm going to take my original function, which was x cubed minus 1, and I'm going to set that equal to the value of 3. And what I want to do is I want to see what x value is going to map to 3. So I simply need to solve this equation. So I could solve this equation first by, I add 1 to both sides. Adding 1 to both sides is going to give me 4 is equal to x cubed, like this. And then now I want to find the cube root of both sides. So when I find the cube root of both sides, that's going to give me that x is going to be equal to the cube root of 4. And I'm going to express that in exponential form. Okay. Then the last thing I need to do before I plug in all into my formula is I need to find the derivative of f. So what is f prime of x going to equal to? And here, this is just, I just want to differentiate x cubed minus 1. So I use the power rule, right? So you bring down the 3 and you subtract 1 from the exponent. And then the derivative of a constant is just equal to 0. So let's put plus 0 there. So in the end, my derivative is 3x squared. Okay. Finally, I need to just plug it all into my formula. So for this last step, we know that the derivative is going, f inverse prime of 3. We know that I want to look at the reciprocal, so that's 1 over. We're going to have f prime of f inverse of 3. Now in my case, I've already calculated what that inside part was. That inside part is 1 over f prime of 4 to the 1/3 power. And since I've already calculated what f prime is, I could substitute in the 4 to the 1/3 into the f prime. So this would be 3 times 4 to the 1/3 squared. Okay. And then I could simplify this a little bit. This is going to look something like 1 over 3 times 4 to the 2/3 power. And if you want to, you can, pop that into a calculator. If you needed a numerical answer, I'm just going to leave it as it is. So this basically concludes our discussion about the derivative of the inverse at a point. And just as a reminder, if you're only concerned about the slope at a single point, you do not need to actually find the inverse. You can just use this formula.